Hello there and welcome back to this video series on control systems. Over the past 2 or 3 videos, we have been looking at MasonsGain formula and its usefulness. We have seen that once the signal flow graph is drawn, finding transfer function between any input and any output is just a matter of identifying loops and forward paths. The outcome of this video is that after watching this video, you will be perhaps able to apply signal flow graph and MasonsGain formula to find the gain between any input node and any output node in a signal flow graph. Having said that, I would strongly encourage you to watch videos 26, 27 and 28 thoroughly. Take notes and keep them handy before going through this video. With that said, let us look at an example and conclude this video. The example that we are going to consider is shown in the picture below. You have two input nodes U1 and U2 and one output node C. We are to find the transfer function between U1 and C. That is, we need to find the transfer function C over U1. So we'll focus on all the forward paths that are going from U1 all the way up to C. Similarly, if you want to find out the transfer function between U2 and C, you will count the forward paths that are existing between U2 and C. Let us do that systematically. Okay? Let us count the forward paths, list them and note down their gains. Let me show forward path 1. Forward path 1 goes like this: from U1 to X1 to X2 to X3 to X4 and then to X5 and then to C. And we can look at its gain as listed here: 1 multiplied by 1 by s, multiplied by beta, multiplied by 1 by s, multiplied by gamma, beta gamma over s square. Okay. Let us look at the second forward path. Second forward path is shown over here in golden color: U1 to X1 to X2 to X5 to C, and its gain is alpha over s. Now we'll try to identify what are the loops present in this signal flow graph. Let us look at those loops. But before that, let us note that capital N is 2 because we have two forward paths, P1 and P2. Let us go and look at the loops. Okay. Let me show loop 1. Loop 1 is X1, X2 all the way back to X1. And its gain is minus alpha over s. Similarly, let us show this loop 2, X1, X2, then X3, then X4, and then back to X1. And its gain is minus beta square over s square. You can see 1 over s, beta over s square multiplied by minus beta is minus beta square over s square. Now let us see the third loop. The third loop goes from X3 to X4 back to X3 and its gain is minus gamma over s. We can clearly see that this loop 1 and loop 3 are isolated. They are non-touching loops. They don't have anything in common. X1, X2, X1 here, X1, X2, X1, then X3, X4, X3. They have nothing in common. So we note that only loops L1 and L3 are non-touching loops. Therefore, we can write delta to be this. We have noted delta. We'll put all the details on one slide for convenience. We note the loops L1, L2, L3 and then we identify what are the forward paths P1, P2. Okay, and write the MasonsGain formula. Because capital N is equal to 2, you have C over U1 is P1 delta 1 plus P2 delta 2 divided by delta, which can be simplified as shown over here. In summary, we see that MasonsGain formula provides an elegant algebraic, combinatorial, and visual tool that will let us compute any transfer function in a set of equations in one stroke. Unlike in block diagram reduction, we don't have to go through any reduction steps. Okay, we have seen two examples so far in this video series, and then I think that's all we have for now. Have a great day.